Thank you, everyone. Thank you, everyone, for coming to my talk. I'm a postdoctoral associate at MIT. I did my PhD before my postdoc at National Institute of Scientific Research in Canada. My PhD work was mostly focused on modeling, analysis, and design of multi-channel cognitive radio networks. But then I decided to change my work in my postdoc to network localization. What we are doing now in MIT is basically ubiquitous and precise network localization using OFDM, MIMO, OFDM waveform signals for different applications. But anyways, this is the last chapter of my PhD. So I'll be talking about this today. It's optimal auction-based resource allocation for 5G networks. Before starting to talk about my contribution in this work, let's talk about a little about the history of wireless communication and cellular communication. It all started back in the 80s with the first generation of wireless communication. It was able to support voice service. It was the first analog cellular communication, 14.4 kilobit per second. I'm not even sure what we could do with that data rate back then. The second generation came around 90s, commercially known as GSM. The first digital system able to support voice and data with the download speed of 144 kilobit per second, and the first time division multiplex system. The third generation was able to support data, much more upload and download speed based on the CDMA technology. And finally, the LTE, which is the fourth generation, is the only purely basically packet switch technology, IP technology, with much more data rate based on the orthogonal frequency division multiplexes, providing many different features, including the seamless handover. If you look at the total traffic growth over the past decade, you'll realize that the big portion of the traffic has been due to the mobile data, and this proportion is even increasing, meaning that mobile data is comprising a bigger part of the traffic in our cellular networks. As we go towards the 5G networks, the traffic is going to increase even further. And the reason for that is basically the fact that we're going to have new subscribers to the network. Further to the fact that we're going to have handheld devices connected to the network. We're going to have connected cars, connected devices. Our appliances in home are going to be connected to the network, as well as the sensors, actuators in our power plants in different factories, which can be which can communicate with our networks. As we go towards 5G, if we have an operable 5G network, numerous technologies and numerous applications will emerge. Wearable technologies are the first in the line. We're going to be connected, all of us, probably, to the hospital. Our health situation are going to be monitored very easily, because at the moment the bottleneck for the wearable technology is communication system. Video on demand is going to be offered with an unprecedented quality. Learning platform will be in place. We're going to.
When you say the bottleneck is communication, you mean the physical layer or the network?
Yes, the physical layer communication.
Do you really think it's the actual physical layer, or do you think it's actually the network?
I'm not familiar with the network side of the problem, but probably we know that there is so much bottleneck. There's so much problem.
But you just said bottleneck is, so you should quantify. How do you know the bottleneck is that and not the network?
Yes, we know that in terms of the bandwidth, there is so much problem, and in terms of the communication overhead for these devices. But you might be right. I mean, in terms of network, there might be other bottlenecks. Okay, that's okay. So video on demand, learning. We're going to have a smart cities. In the sense that traffic lights are going to be connected to the network, so that we can spend less time behind the lights. We're going to have the smart grids, in the sense that the power meters, gas meters will have the platform to provide to increases the efficiency, and also real-time communication and things like virtual group activities. So before talking about the challenges, basically let's talk about the challenges at this moment. For the 5G network, we have to address a number of issues here. The first issue with 5G is the coverage. And the coverage in 5G network is important because these devices that we are talking about they are, It's not like the handheld devices that we have, that we can, for example, relocate, go to a new place in order to have the coverage. These devices, they are wall-mounted devices that, that are located in different areas, for example, in remote areas, let's say in the basement of our buildings. And these devices, we should be able to provide coverage for these devices in the basement and in remote areas. Let's say, for example, we have sensors and actuators that are located in power plants where previously it didn't make justification for the operators to provide coverage in areas outside of the city. The traffic diversity is the second problem with 5G network, in the sense that these devices, they create traffics that are absolutely different and provide, the different levels of traffic exigency. And also there is the traffic scale that increases, and the battery endurance. So we believe that the spectrum allocation is the important part of the 5G networks, and it has to be addressed. The most important factors that we have here for 5G is delay. We should have a small delay. We should have higher rate. The increase in capacity is so much, it increases by 1,000 times more. And also the power consumption decreases so much. In order to satisfy these requirements, we should have directly reflect these requirements into the allocation mechanism. We need an allocation mechanism that allocates resources on a microsecond scale. We need to have an allocation mechanism that is adaptable, and which means that it has to be load dependent, channel dependent. It has to depend on power consumption level of these devices, and it has to depend on the mission. The communication overhead of the allocation mechanism is so important, because we want to have a low communication overhead for allocation mechanism, despite the fact that at this moment in 4G networks, there is so much handshaking between the base station and devices, and this consumes so much bandwidth. The optimality is another important perspective of the allocation mechanism, because we have a limited bandwidth in 5G network. We will be offered 10 times more, probably more bandwidth because of the millimeter wave, but we are expected to increase the capacity by 1,000 times more. So we should be increasing the spectral efficiency. And finally, the fairness is a very important property. All these requirements, if we want to translate them into, meaning that if we want to satisfy those requirements using the existing frameworks, this is not pretty much possible, because the computational burden of the existing allocation and scheduling mechanisms in 4G networks is not so good. The communication overhead, as I mentioned, there is so much handshaking between the base station and devices, and the optimality is not so good. As we all know, the scheduling mechanism for 4G networks is basically a simple weighted sum algorithm that takes into account the channel state information. It's not load dependent. And the power consumption, obviously the mechanism doesn't take into account the power consumption of these devices. These are battery operated devices, and any allocation mechanism for 5G has to take that into account.
So are you stating that the computational burden in the future when 5G gets deployed will not be able to handle the same level of 100,000 X variables?
We believe that, yes, because
and that's because 5G is going to have more variables, more users?
No, this is the idea. What I'm saying is, if we want to satisfy these requirements using the allocation mechanism that's currently we have in LTE networks, the number of devices are so much higher that the allocation will not be able, the mechanism will not be able to resolve the problem, the maximization problem, in such a limited time, which is microsecond scale problem.
I wonder, because NVIDIA just announced today that's coming out with a box, all right? And the box that they're going to have has enough GPUs in it, and it's about this big. And it'll have the computational capabilities of 400 compute servers.
You mean for the base stations, right?
Yeah, why not deploy one of those things? I mean, what's happening is you got another revolution, another sort of inflection point in computation.
Right.
It could change that statement, so
Right,
might be worth considering in the future. Just
the thing
computation
is,
might not
right.
be a problem if we have mega compute servers available. So
I can add something to that. We don't really know what 5G is going to look like. 5G can be anything. Any of these companies, they are working on some sort of solution. And probably the device you're talking about, what I mean here is if we want to have a fully adaptable scheduling mechanism that depends on the load, meaning what traffic is being created. If a device doesn't have a traffic, it shouldn't be allocated anything. It should depend on channel, it should depend on power state or battery state of these devices. It should depend on the kind of mission and many other factors. If we take all these into account, we believe that the allocation mechanism, the scheduling mechanism that currently we have in LTE networks, it's basically impossible to resolve this problem in microsecond. It's not even in microsecond scale, because microsecond is the interval of between 2 frames. So there is communication overhead, there is the computation, there is the propagation time between devices. I'm not sure if what that is, that module that you're talking about.
it just wasn't
But
today,
yeah,
so
that was a
the
good
point
point.
is that there's a huge inflection
Right.
happening.
Like companies are working in this area, obviously. I know Ericsson is, for example, releasing the first 5G platform, base station platform recent. I mean, in 1 or 2 months, this is what they have. So, so basically, the idea is these requirements we believe are difficult to address using the existing frameworks. The solution that we propose lies in understanding the nature of the futuristic devices. These futuristic devices, they are powerful elements that possess so much processing power. They are smart, meaning that they have analytical power in order to learn, in order to perceive the environment. And these devices, they are smart in the sense that they can predict the future needs that they have based on the past experience that they had and the current situation that they are located in. Most importantly, these futuristic devices, they are context aware in the sense that they are closest, in a very simple language, they are closest to themselves. They are closest to the field. They know their own battery level. They know the accuracy that they require. They know the criticality level of the traffic that they have to submit. They know the delay requirements, connectivity, maintainability, and finally, they are task-oriented. So our idea is we have to change the paradigm for the allocation compared to what we have at this moment for the 4G network, which is a very basic weighted sum sort of weighted sum algorithm for proportionally dividing a spectrum between nodes. The new paradigm, we believe, is about auction mechanisms. Auctions are centralized mechanisms that at the same time that they're centralized, they have so much decentralization in them. They're simple to run, they are generic, meaning they can be used, they have been used in the history for the allocation of commodities to different people and different users, let's say. And in this case, for the allocation of bandwidth, regardless of the traffic at node type, and also it creates the efficient outcome. In communication context, we know that auctions have been applied, have been used basically by FCC in order to lease big chunks of a spectrum for long-term uses. Some of these actually operators, they have had the spectrum for more than half a century. But now what we want to do is to bring this idea one level down in order to allocate a spectrum to the devices on a microsecond scale. But there is a question here. What kind of auction are we going to use? There are 100 different kinds of auctions. We can't even name all of them. We have seal bid auctions, we have English auction, we have Dutch auction, we have Vickery auctions, which is, again, second price auction. And the other thing is, even though we are able to choose an auction here, there is a revenue equivalent theorem in very celebrated theory, in game theory, that tells us that all these auctions, they create the same amount of revenue when a certain number of conditions are met. For example, when the valuations of devices are independent, they are drawn symmetrically from a symmetric distribution, and the devices or bidders, let's say, they're risk averse. So, especially for selling a single unit of bandwidth, let's say, all these auctions, they create the same amount of revenue. So we cannot talk about optimality or the superiority of one auction versus the other. The good news is, in the area of multi-units auction, this properties mostly doesn't hold. And because revenue equivalence theorem doesn't hold in this situation, what happens is that then we can talk about which auction is better than the other auction. So auctions, they create different amount of revenues, and because revenue in macroeconomic theory is directly related to the efficiency of the allocation, we can talk about the optimality of resource allocation or allocation of the bandwidths. So the idea that we have here is to use optimal multi-unit auction theory in order to satisfy a number of axioms here. And these axioms are going to be embedded into the mechanism. We want to allocate the bandwidths to the devices who value the bandwidth the most. And this might seem a little bit counterintuitive for you to talk about valuations for devices, but the idea is we are talking about devices that can process, that can, that can deduce, that can decide. So these devices that can, perceive the environment and make independent decisions. So they value the bandwidth differently depending how much they value the spectrum. This increases the efficiency because this is the most important definition of efficiency in macroeconomy. These devices, we want them to leverage their abilities in analyzing, deducing, and deciding in order to lower the computational burden. We don't want to deal with everything as the basis station. We want to basically receive just how much the information that how much bandwidth these devices require, and then decide how much bandwidth we have to allocate to them. We want to let devices decide what they need, how much they need, and why they need the bandwidth in order to emulate adaptability. We want to force them to abstractly represent their needs so that there is no communication overhead, so much communication overhead that, for example, at this moment we have. In order to, for example, multiple handshakes that goes back and forth between base station and devices in order to just make them know that, let them know that this is the bandwidth that you have to receive. We want to enforce truthfulness. This is essentially important to the multi-unit auction mechanisms because the devices, they can misrepresent their valuations. We don't want them to be not truthful. We want them to reveal how much value they value the bandwidth so that we can increase the optimality. And I will discuss this in more detail in a few slides. And also we want to charge devices that receive more bandwidth more money. And also to maximize the total collected revenue. So this work was actually inspired by, I would say, one of the greatest minds of microeconomic theory from Harvard University, Eric Meskin. He was awarded Nobel Laureate Prize a few years ago. For really like his significant works in this area. So before talking about the details of the allocation mechanism, there are a number of assumptions that we have to discuss here. These assumptions, well, these are rarely assumptions as they are the properties of any competitive market. You might have heard about these properties as I go through them before, but again, I call them as assumptions here, and they are related to the demand profile, or you might know this as demand supply curve. The first assumption says that it is the law of demand, which means that as the bandwidth increase, as the demand for bandwidth increases, the prices that devices are willing to pay decreases. Meaning that it's like it has negative slope, the demand profile. And also as the valuation of devices for the bandwidth increases, the price increases. The second assumption is about the valuations of devices for the bandwidths. These valuations has to be symmetrically drawn from a distribution function that is continuous and twice differentiable. And the upper bound cannot be infinity, lower bound cannot be minus infinity. They should be the minimum and maximum valuation of each device has to be within a limited number, basically. The third assumption is about the demand elasticity, which can also be reformulated in the form of risk aversion, which in a very simple language tells you that as the valuation of devices for the bandwidth increases, these devices become less reluctant to participate. They become more risk neutral, or probably more risk seeking, let's say. And this is a very intuitive idea, because as the valuation increases, these devices are willing to participate more and pay more. And finally, the final assumption is about the demand saturation, which is shown here. So in words, the allocation mechanism works as follows. We have devices who have diverse valuations, nu I, for the bandwidth or for the power, let's say. And these valuations are private information. They are not known to each other. This is not a colluding market, and we assume that these devices, they don't share their private information. They receive the sensory information from the environment, including, let's say, these are 5G devices. They receive information about the status of their batteries, how much it is depleted, how much it is left. They receive information about the channel, wireless channel. What's the fading status of wireless channel? They receive information about the nature of the traffic. They predicted the traffic, and they realize that, okay, probably in 20 minutes, I'm not going to receive any traffic, so I don't need to bid. I don't need to participate in any auction to receive any allocation. So this is basically, these information are summarized to announce the amount of resource they require. We represent that with BI tilt. And these information, these bidding strategies are announced to the base station. The base station, upon receiving these bids, which are the amount of bandwidth basically that the devices claim to require, it estimates the valuations of devices. And this state is very important, because without knowing the valuations and without estimating the valuations, there is no way that the truthfulness can be induced into the mechanism. Based on the estimated valuations and the received demanded bandwidth, the demand profile is updated through a learning process. And finally, the beliefs are updated. And we need the beliefs, as we will see later on. I will give the details of how these are done. And finally, we calculate the optimal prices. The base station calculate the optimal prices and allocations. These are allocations, these are optimal prices, and declares these information back to devices. And devices, upon receiving that, can use the frequency and the bandwidth to transmit the information until the next round of auctioning. A number of definitions are in place. The first one is device revenue. We define device revenue as, well, this is commonly known, like this is a very common definition of revenue. It's the area under, the mathematical area under the demand profile for the bandwidth that was allocated and for the valuation that is a private information for the device. We define the device utility as the device revenue minus the amount of money that the base station charges that device for the amount of resources it was allocated. Or we take this, I mean, we do, this has to be done, this we have to take the expectation basically, because, well, the amount of utility of each device is not known. And it depends on the valuation of other devices, because this is a competitive market. So we take the ex interim expectation in game theoretic language with respect to other devices' valuations. We define the truthfulness behavior to be the dominant strategy of the game by saying that by being truthful, devices, they accrue the maximum amount of utility. So truthfulness becomes the dominant strategy of the game. Devices, they have no motivation to unilaterally deviate from a truthful behavior. So they reveal their valuation as their bidding strategy. On a very related note, we're going to talk about...
Do you actually, how does one know one's own valuation?
Yes, we have to estimate that. The base station...
I like coffee.
Okay.
I like it a lot.
Okay.
She likes coffee too. How does one quantify my valuation of coffee versus her valuation of coffee in a unified notion of how we value coffee?
Based on the behavior
these
that...
are just numbers, all right? I mean, how do you put it into something that we can actually quantify, or a provider can quantify, or I guess in this case you're talking about devices, and that's a real problem. I mean, I get that they're variables.
Right. I will explain that that's the core idea of multi-unit action theory is this: how we can estimate the valuations based on the behavior that you exhibit as a bidder, because you are constantly sending information, and we have the demand profile. We have to update the demand profile of the base station, as well as the fact that there are probability density function of the valuation which has to be updated constantly. And the core idea, we're going to get there. The core idea of multi-unit action theory is this: to find the pricing in such a way, to charge users in such a way by the prices that this relationship is satisfied. We will see that. We will get there. But very good question. I mean, this is the core idea, as I said, of optimal multi-unit action theory. So on a related note, the revelation principle tells us that revelation principle is, I would say, the most important, probably one of the most important, principles in game theory. It says that if we have a mechanism that produces an outcome A, the same outcome can be produced through a revelation mechanism, meaning that there always exists a mechanism called the revelation mechanism, where devices they have no tendency, they have no propensity to lie, and this mechanism can create the same amount of output than any other mechanism. So the mechanism, in other words, lies for us. We don't have to lie to the mechanism. But the problem is finding this mechanism is difficult. This is just an existence problem. This doesn't tell us how to find the mechanism at this moment. But let's assume the key idea here is, if we have a mechanism out of nowhere that induces truthfulness somehow, meaning we have a leverage to be able to induce truthfulness so that devices, they have no motivation to deviate by misrepresenting their valuations, then in this case, if we search through the class of direct or revealing mechanism, truthful mechanisms, and find the optimal mechanism, then this mechanism is going to be optimal among all classes of actions. You can see that. This is quite intuitive, right? Because the assumption is that, and we have the revelation principle. So, but the question then becomes, can we find this? Can we somehow put ourselves in the world of revelation mechanisms, or direct mechanisms, alternatively called? And the answer is yes. We can find the revelation mechanisms. This is the answer to your question. The revelation principle, based on basically this is the finding of multi-unit action theory. It tells us that if devices, or if basically bidders are charged with prices that are defined with this relationship, and Ri is the revenue of a device or a bidder, and Ri with this notation is the second derivative. If we can charge devices on this basis, and also there is the efficiency requirement, meaning that if a device values the spectrum more, it will be provided with more amount of a spectrum, then we're going to be in the world of truthful inducing mechanisms. Now that we are there, according to this, we will find the optimal allocation mechanism in this class. So that then we can claim that this optimal allocation mechanism is the optimal in all classes. The optimal allocation mechanism in the base station side is formed by maximizing the ex post, somehow in game theoretic sense, amount of prices, the prices that are collected in each auctioning round from devices under a certain number of constraints. And if we can maximize this, then this optimal result is basically the optimal result of allocation among a very big class of auctions. And this is a very broad sense indeed for the definition of optimality. And but the problem is, can we solve this? Yes, we can solve this if we put a very mild constraint on the choice of the probability density function of the valuations, which is called the regularity assumption. So if we have the regularity assumption, then this problem becomes a convex problem. Oh, it becomes a quasi-concave problem indeed. And then we maximize this quasi-concave problem by applying the KKT condition, which you might all be familiar with. So we don't have to solve the maximization problem directly by searching through the space of the input variables. And we will be able to find the maximum, the answer to this. And the answer is going to be a system of linear and nonlinear, a system of semi-linear equalities and inequalities. And this is the problem on the side of the users. So the base station tries to maximize its own utility. How about the users? The devices will maximize their own utility, which is basically they maximize their own revenue by finding the revenue maximizing strategy, which also depends on the valuation. And in this work, the valuation of each device, I characterize this based on the expected spectral efficiency. If you are from telecom background, you will see that the spectral efficiency, the average one, depends on the instantaneous spectral efficiency, somehow depends on symbol error rate, and many other factors. But the revenue in 5G devices or in any independent device or any element that can make a decision can be a function of different factors. For example, the valuation of a device can be anything. It can be a function of a spectral efficiency. It can be a function of power consumption. It can be a function of fairness and many other factors. So this maximization problem has to be solved on the side of the devices. Now, I want to summarize. In motion, what happens is this. Devices, they maximize their revenue by finding the revenue maximizing, basically, a strategy, how much bandwidth they need. They don't have to, at this moment, request the total amount of bandwidth they require. They might believe that, okay, based on my utility that I formed, I might better to just postpone the amount of bandwidth I need, just request 10% of the bandwidth, and then maybe in future, 2 auctioning rounds from now, 10 auctioning rounds from now, I will be able to get lower price for the bandwidth. And then, based on that utility, BI, B1, B2 to Bn is obtained. It's declared back to the base station. The base station receives the total amount of bandwidth that requested bandwidth that it received. 2 situations may happen. The surplus situation is when the total bandwidth available to the base station is higher than the sum of the requested bandwidth. The other case is obviously the deficit, meaning that the base station cannot cater to that requirement, so it has to somehow adjust the bandwidth request. In the case of surplus, by solving the maximization problem, this is going to be the system of equations that we have. The base station will be able to provide whatever the devices requested, so it can cater to that. But it has to follow this rule, this pricing rule, in order to be able to induce truthfulness, meaning that devices, they won't have any motivation in order to deviate. But in order to do that, valuations has to be estimated. And there's a simple formula, not a simple formula, a nonlinear formula, but a function of a single variable to be able to find the valuation. So this is the amount of bandwidth that's dedicated. It's plugged here. The valuation estimation is found, and this equation is used in order to charge the devices based on how much bandwidth they receive. In the deficit situation, things are more complex because in this situation, a readjustment is required. Again, this is a constraint, meaning that the total bandwidth should go, nothing should remain because of efficiency, obviously. We estimate the valuation of devices. We charge device, before going here, we estimate the valuation of devices. We use these nonlinear equalities in order to find the allocated bandwidth. And finally, what we do is that we use these charging formula in order to charge devices based on how much they received. And the allocation is declared back, as easy as that, to the devices. And devices can transfer until the next auctioning round, where happens another microsecond later on, in order to decide how much bandwidth has to be allocated to a given node. Some results for a very basic case of something that all of us can visualize. These are users. It can be handheld devices. It can be anything. We assume that the experimentation happens for 1,000 times. Very simple scenario where the demand profile is linear. It satisfies the assumption that I mentioned. It's increasing with respect to the valuation. It's decreasing with respect to the demand-supply relationship as we all know it. The amount of bandwidth that's available to the base station can even be a random variable. So this can even be applied for the scenario of cognitive radio networks when the base station doesn't know anything about how much bandwidth it will have in its possession, let's say one second from now. So even W0 is a random variable. The valuations of our devices, we assume that we know it. It's an exponential distribution. And we assume that the strategy space is a linear relationship, has a linear relationship with the evaluation of devices. So we solve the problem. This plot tells us, I'm sorry, the quality is very bad. It's allocated bandwidth are the red dots, and the demanded bandwidth are the blue dots. Because we have a capacity here, everything has to be damped down. If you look at here, you see that the allocated bandwidth to the secondary user or to user number 1 and to the user number 2, it has some form of uniformity, meaning that we were able to satisfy the fairness requirement. Even though you might be able, if you want to readjust the valuations, you might be able to give some level of criticality to some users in order to, for example, concentrate this mass of allocation more towards here or more towards here. This is possible. So we can somehow differentiate this, as I will explain in few slides from here. These two plots in the middle are empirical probability density function of the allocated bandwidths as well as the valuations. The valuations, we assume that we know, but device, they don't know each other's valuations. So this is the ground truth, the blue one. And this is the valuations that we estimate. And obviously there is a mass of valuation here because we are assuming that our probability density function for the valuation is somehow bounded, upper bounded, and also lower bounded. But our lower bound is 0, our upper bound is here. So there is a good match here, and also the allocated bandwidth versus demanded bandwidth, as long as we know that, as long as the amount of bandwidth that's available to the base station allows us, we're going to be able to follow this very closely. And this is the total sum of the collected revenue for the base station. Several remarks are in place. The first remark is, well, so far, we didn't set any restriction on the nature of the allocation units. As long as there is granularity and some sort of, the commodity is divisible, it's not indivisible. As long as we can do that, we will be able to use this allocation mechanism to allocate different kind of resources. For example, we can allocate power if we have different levels of power for example, CDMA systems. We can allocate time slots in TDMA. We can allocate resource blocks, RBs, in OFDMA systems. So this is the first thing I wanted to emphasize. The second point is that so far, we know that the efficiency of allocation, an allocation mechanism is efficient, all of us we know, if it can be adaptable to everything. But we cannot make it adaptable to everything, obviously. We have to make it adaptable to the most important factors. The most important factors are channel state information, basically, and load, meaning how much bandwidth a device requires. And if it doesn't require so much, it doesn't have to receive so much. If it does require so much, it has to receive so much. And the thing is, in 4G networks, the allocation mechanism is only channel dependent. We want to make it kind of load dependent as well. And also, the other thing is, so far we didn't discuss about the channel dependency of our allocation mechanism. So we have to add that flavor to it as well. We do it by readjusting the initial valuations that we were able to obtain, using a modifier matrix, and this modifier matrix can be the channel state information matrix, for example, in LT systems, as easy as that. With diagonal elements filled with, with the channel state information between the base station and a user, and the other elements are 0. This way, the initial valuation, they reflect the load dependency, and this matrix, it reflects the channel state information. So higher valuation is going to be experienced here when both both the initial valuation estimations are higher, and also the channel state information is better, meaning that, for example, the device is closer to the base station. We can even go one step further by putting these non-diagonal elements to non-zero values in order to somehow oppose the idea of collusion between devices, even if that's possible. This way, we're going to be perturbing somehow the motivations of devices to somehow changes the valuations in a direction that they can, for example, achieve more bandwidth for less amount of money. And by setting these values to these non-diagonal values to non-zero amounts, we will be able to achieve that. In terms of network integration, just a very brief discussion. How can we integrate this idea into, let's say, LTE network, into 5G networks? We really don't know, as I mentioned at the beginning of this talk, what 5G networks are going to look like. Every company is talking about a different sort of technology, but there is a consensus that 5G is going to be OFDMA based. So I will talk about embedding this mechanism into LTE networks, and also, for example, WRANs, wireless regional area network, which is also OFDMA based technology, but with a different size of frame. What we do is, we have in OFDMA systems like LTE, we have an upstream subframe, downstream subframe, and allocation subframe. What we do in order to integrate this mechanism is to use the common control channel, which is available. It's currently being used for controlling purposes, and send 3 subintervals over this common control channel. The bit subinterval is used in order for the devices to find a revenue maximizing strategy and declare those at the same time to the base station. The tentative allocation is used so that the base station, which was able to find the optimal allocation and prices, to declare those to the devices. And finally, depending on the fact that devices received something that they requested, or they didn't receive what they requested, meaning in deficit situation, they might be able to refuse or accept what they were offered. And this is as easy as a 3-way handshake, meaning, it doesn't even have to be discussed, but allocation mechanisms through auctions are generic for this reason, because not so much information that is irrelevant will be communicated between base station and devices. So, to conclude my talk, we propose an auction-based allocation mechanism for 5G networks that can deal with diverse traffic requirements in terms of scale, in terms of the diversity of the nature of traffic, and it solves many of the problems that at this moment the scheduling mechanisms are dealing with. The theory of multi-unit auction theory has been leveraged, and the proposed mechanism has these axioms, these properties. It's efficient, meaning that it allocates a spectrum to devices that value the spectrum more. It's fair, meaning that it charges devices that receive more spectrum with more monetary payments, or non-monetary payments, let's say. It's revenue maximizing, it's easy to operate, immune to collusion for the reason I just explained. It's computationally manageable because we are not solving a maximization problem anymore. What we are doing essentially is just to solve a system of linear and nonlinear equations, semi-linear equations. And it requires low computational overhead because there is not so much handshaking between base station and devices, and most of the thinking is being done on the side of the devices rather than kind of outsourcing most of the decision-making process to the side of the base station. And it provides a stable solution. A number of future...
So, sorry, going to add that quick question.
Sure.
So, you mentioned the microsecond time scale for this. My understanding was that MagClear would be operating at a microsecond time scale, and anyway it is doing some kind of allocation. But does the spectrum need to be traded at that speed? Would it be milliseconds or seconds perhaps? Because that's the rate at which the demand actually changes.
at this moment, what happens in LTE networks at this moment, we know, is that the frame length is in the order of milliseconds. It's 1 to 10 milliseconds at some points. And these allocation intervals, the best, like the network does, is to put the allocation, allocation in the preamble of the base of the LTE frame. So the fastest interval that we know at this moment between two allocations is no less than 1 millisecond.
It's of the order of millisecond. Right?
At this moment is in the order of millisecond.
But my question is, will you benefit by putting it in at every opportunity, or perhaps once every 100 or 1,000?
The idea is we have to make the allocation as adaptable as possible. GSM was allocating TDMA time slots in the order of tens of milliseconds, not hundreds. Then it became LTE. It became milliseconds. And there is a reason behind this. The reason is the faster we can do this, the more we can deal with the fluctuations, for example, in the channel, fluctuations in the load, different unpredictable factors. So there is definitely advantage in allocating the resources more often. This is a unanimous kind of agreement between.
I mean, I think that's true in general, but you can do a study to see, does it really help me to do it at once every second, once every hour, once every minute, To me, it seems like the scale of time constants is not going to change that much because of human activity or changing weather patterns or things like that. They don't change at millisecond time.
But the channel changes in that order. So in physical layer, when you're talking about the channel fading.
Right, but that is getting absorbed by the scheduling and MAC function, which is a big.
Yes, that really could be a research avenue to understand really like how important this is.
I can see that you can do it as many times as LTE allows.
Right. Very good question. So I'll summarize this, then I answer your questions. So a number of future research directions for people who are interested in the field. The first thing is, we talked a lot about estimating valuation distribution. Like we didn't even talk about that. We assumed that the valuations of devices are available in the form of a symmetric distribution function, probability distribution function. This is actually CDF, but anyways. But there should be a way that we have to be able to estimate these. And there are ways that is being done currently in a very crude manner in different markets in order to be able to find the valuations of devices. There could be much better results if we can use the inference techniques and the Bayesian methods in order to be able to obtain a more precise characterization of the characterization of the probability density function. Because at the end of the day, if we don't know this with precision, the entire allocation mechanism is going to drift from its optimal point. Because we are taking expectations in x interim and x antisense, and these probability distribution functions are absolutely essential for the accuracy of the problem. So this is one interesting problem. For wireless communication systems, you will have to understand what the valuation of devices are, and then characterize these valuations functions. The second problem, future direction, is the regularity assumption. I assume that there is a regularity assumption. I didn't go into the detail of that, to be able to convert the optimization problem on the side of the base station to a convex problem so that we can apply the KKT condition. But the problem is we might not be able to have this assumption. And this assumption, indeed, is a very important assumption in the sense that it is related to the inner qualities, because these inner qualities are related to the valuations of devices. But at the end of the day, valuations of devices are somehow related to the past experience of this device, meaning how much bandwidth it was allocated or how much it was charged. So there is a magical link between the valuations of wireless devices and the past history of their allocation. And one future direction can be figure out that magical link in order to be able to influence, in order for the base station, again, to be able to influence the regularity assumption so that this assumption always holds. The third research avenue is to characterize revenue function of devices more realistically, obviously. Because what I did was in this work, I characterized the revenue function only based on the expected spectral efficiency. You might want to consider other factors too, which is very important because 5G devices, they might have different factors for their valuations. And finally, the complexity analysis is in place because I assume that, well, the problem is easy to solve because it's not maximization problem anymore. But in this situation, if you want to be more precise, you might want to consider, what's the computational complexity of solving this problem, and because this is, at the end of the day, this is a linear and nonlinear sort of system of equations, and the complexity obviously grows with the number of devices. And finally, finding the demand profile is very important. This is, again, something that I assume to be given, and I updated that in every auctioning round. But again, we need ways to understand how to characterize this. So that was my talk. I hope I didn't bore you. I'm ready for questions.
Get the light back on.
Yes, thank you. Interesting talk. I'm thinking back at the question that this coffee drinker over here raised at the beginning. And how do you quantify the value of something like coffee? And I was thinking in my own mind that, well, whenever two coffee drinkers come up to the vending machine, it should hold an auction and see, who's willing to pay more for the cup of coffee and sell it only to the highest bidder. But then I think about your comments about granularity. And I thought, well, if only one person at a time comes up to the vending machine or the base station to auction off some resource, then they would always get it at perhaps zero price. So if the granularity is too small, the arrival rate of the coffee drinkers or the devices would always be could presumably be at a point where they are there's no excess demand, and they would always get the zero price. But if instead you say that that everyone has to stand in line for a minute before we hold an auction or until we have some excess demand,
right.
Then we would find that there's real value associated with it, not zero. How do I think through, what mistake am I making here in thinking that if you just turn down the granularity or the time interval low enough, it would always go to zero, the price?
So the more competition you have, obviously, between devices, the less price are going to be observed. Meaning that because of the demand profile relationship that I mentioned, the assumption at the beginning, once you have higher demand for the bandwidths, we assume that the price for that bandwidth decreases. And for that reason, as soon as the price
supply, the higher the demand, the higher the price.
The higher the demand, the lower the price.
For a fixed supply.
For a fixed supply. That's the law of demand, right? It always happens. Like as soon as there is more demand, the manufacturers they decrease the price.
That's why I'm saying a fixed supply.
Yes.
Yeah. If there's only one cup of coffee, or if there's only 1 megahertz of spectrum, then there's a fixed supply.
Right.
And the more people who are demanding it will drive the price up.
The more people who are demanding it, it can't be like that for a reason.
Check an art auction at Christie's.
Right.
That's how it works.
Exactly.
Right.
Yeah, yeah, the
Christie
second
likes to have
transaction.
more
Yeah.
people in the audience to drive up the price.
Exactly.
So if we have more bandwidth demand here, what happens is that, okay, now I got it. So if we have more bandwidth, the valuation of each of these devices, so at each moment of time, we are in one of these curves. Each of these devices, they are in one of these curves. Devices, they don't know each other's curves because these curves, they are the valuations of each device. So for example, device number 1 is operating on this curve, device number B is operating on this curve. And because the valuations are hidden from each other, these two devices, they don't know on which curve they are located. So as soon as the demand increases for the bandwidth, we say that the price decreases. You are saying that the price increases because the competition increases. But the valuation of the devices for the bandwidth decreases when there is more competition. So the valuation drops, the demand falls back.
What's the x-axis there?
The axis. This axis is the spectrum demand. This axis is the unit price for that demand.
Wow, we're having trouble with definitions or something. I don't know any market where when you have more people that want something, the price goes down. So there's just a fundamental, and we're not talking the same language
More
here
people
somehow.
want something means more demand.
More demand means there are 6 people that want this 1 megahertz of spectrum, not 2. So I can sell it at a higher price to whoever I'm going to sell it to. It's a non-fungible,
No, I
transient.
think there are two kinds of numbers here.
That's what I mean.
What he's referring to is the fact that when we move from 3G to LTE, the price that we are willing to pay per unit of bandwidth drops. So as your total use increases, the price per unit of bandwidth tends to drop. That's the individual experience.
Okay.
Right? But
That
then
is
there's
the case as well, yeah.
But then there's the global auction where, of course, if there's a limited amount of spectrum, the price would tend to increase as you have more.
My expectation
more
is for the
users.
price to go down because of efficiency of use. You know,
That is the
production.
second
Yeah, so I think that's
Right.
part of
You're
it.
doing 2 steps at once.
I think that's kind of axiomatic for what he's
Right.
doing.
I mean,
But beyond that, of course, if there's a limited capacity, then it's going to raise the price as more people.
The trouble with that argument is that it has in the underlying assumption that if somebody's is only willing to pay less for something, I can make it cheaper, which would imply I get an infinite amount of bits per second per hertz of spectrum that I buy. That's clearly not true. That fails at some point. You go asymptotically at some limit, which is Shannon or whatever your favorite limit happens to be. Whatever boundary condition you're going to put on your partial derivative, that comes in and levels off. And so you can keep making it more efficient. You can drive that curve, and I forget what that curve is called, but there's a curve of efficiency. You double the amount of something, and it goes down 25% the cost. It's a universal curve.
That's exactly the same curve.
Right, right.
This is this curve, right? This is the
That's
demand
not
profile.
demand. It's called an experience curve. That
Right.
you can make something more efficient, and that curve levels out when technology or physics or whatever doesn't let you do any better.
Right. I got it. I got the question. Okay. So I think the background here is you're talking about a monopolist market. This is not a monopolist market, meaning that there is only one seller, and that seller determines everything. Meaning that as soon as the demand goes up, the prices per the unit price has to go up. We are not talking about a monopoly situation. This is what is it called? Oligopoly, something like this.
Yeah, whatever.
Yeah, something
We
like
know
this.
what you mean.
Meaning that there is a competition. So as soon as this, I mean, these base stations, there are thousands of them,
But I
right?
can't beat physics. All the competition in the world isn't going to give me a gigabit a second in 1 hertz of spectrum.
No, it's not going to happen. Yeah, of course. I mean, there is a lower bound than that, right?
Okay, so that curve looks nice and smooth, and I'm putting math into it, but it's got limitations.
Right,
that
I
are
mean-
really hard limitations.
This is not infinity, right?
Okay, yeah.
This is not infinity. This is not going. This is not asymptotically
It's
going.
actually going up faster as you get there.
Yeah, this is the zero valuation.
Right.
I'm sorry. These are very
No, I understand.
shady sort of. But these are. So it doesn't mean that when the demand decreases to zero, so the base, a single device who participated
So it
has to
rolls
pay.
over at some point.
This is just cutting down. This is over. This is the property of market is that the demand profile doesn't go from minus infinity to plus infinity because the valuations and the demanded profiles. This is the valuation. Here we are exchanging the valuation with demand, right?
Okay.
This is what is happening. So the valuation is increasing, and the maximum amount of valuation for each user is here. That's it. Valuation users cannot value the
You're just
bandwidth for
clipping it off.
infinity. There's a cutting edge. There is a bound on this. And the other thing is you're talking about that universal curve. That universal curve is usually this, but most of the times they say that it's a linear, let's say, characteristic behavior. But here, the more bandwidth is demanded, the unit price is going to drop, because if the unit price doesn't drop, I'm talking about the generic market, then there is other seller who's going to sell the same amount for the lower price. Did it answer your question?
Well, he'll sell it if he can. We went through that with fiber. At some point, the cost of selling it is less than the cost of you getting up in the morning and you don't have a market.
Right.
Okay, and that's an additive cost. So it shows up on a log plot here differently
Right.
than a nice smooth function. Well, the question I had to supplement what you were saying is, how do you deal with asymmetry and hysteresis? I mean, it's well known that if you have an object, taking it away from me has a different value than me getting it fresh. Losing $1 is very different from winning $1. Very different
Very
in many
interesting question.
situations. If I'm already running a streaming video and I'm using a certain amount of bandwidth, a little extra bandwidth, who cares? A little less bandwidth, I get really upset. So there's a case where the valuation is highly dependent upon the sign.
Okay.
Am I losing or winning? So these curves are not bidirectional curves. They're adding it to a user and then taking it away, like the cup of coffee. I got my cup of coffee. You're going to offer me a little bit, you can take it away from me.
Yeah. Can we characterize that behavior into this law of demand? Meaning that if you are losing, if you are in the, is that exactly what you said? Can we say this? This still applies, right?
It does. It's just the curves, instead of being curves,
Right.
they have arrows on them.
And this is just for the purpose of illustration, because we didn't put any constraints on the choice of D, except these constraints, right? It can be anything. It doesn't have to be a smooth. It can be, basically, what we can do is uniform, uniform. So here, you're going to have, in several markets, this is the case. There is a uniform demand profile here, where if you receive the amount of bandwidth or the commodity you need, you will pay a price, and the price is exactly the amount of valuations, meaning that valuation is your clearing price, obviously. But as soon as there is more demand, then you're not going to pay anything. So it can be anything, as long as those requirements are met. It doesn't have to be this smooth curve. It can be other kind of curves, and I think that's what you're saying now. In terms of taking and giving, that is exactly satisfied by this equation.
Then you still have, of course, Wade's problem is do people actually know what something is worth? That's really tricky, because there was a bandwidth study in Berkeley done many years ago. I remember seeing it, where they had people in the community were given a knob on their monitor to raise and lower the bandwidth, and also a dollar amount they had to pay for that. So the behavior was what you would expect for humans. They turned them all the way down and complained.
Right.
And so they didn't have they weren't able to get a real sense of what the value was to them.
Right.
And we don't see much of that. Benjamin Franklin had a good essay on that, which is worth reading.
Auctions are really weird sort of mechanisms, because when you read these, history of auction books, for example, one by Joali, an Indian, very famous researcher, he says that. For example, the same thing that happened, for example, in 1930, when FCC was allocating auctions, even to a number of, not so many, to a number of operators, a very different sets of irrational behaviors were observed. These are because we are overly rational. Risk aversion is something that no one can explain. If you are receiving, if you can demand more, and accrue more, basically, utility, what's the definition, what's the justification for the risk aversion, right? There is no reason. It's just the fact that some people they don't want high
Loss
variance.
is worth more than gain.
Yep.
That's what the risk aversion says.
Right.
If I lose this, I will be more unhappy than I will be happy if I gain it.
But if you calculate the expectation of the revenue, you see that the guy
Nobody
is
does
receiving
that.
more money if
Nobody does that.
Right, that's the thing.
Humans. Yeah.
Yeah.
Have you read Daniel Kahneman's book? I mean,
No.
he's an MIT. Oh, you can't be doing this.
Can
and not
you
having
tell
read
me his
that
name?
book. Predictably Irrational. He's an MIT.
What's his name?
Daniel Kahneman?
Okay, thank you.
He did.
Okay, what does he
Anyway,
say?
it's called, the book is Predictably Irrational. I may have gotten the author wrong, but it's Predictably Irrational.
Mm-hmm.
And he's an MIT professor
Right.
that's looking at these issues, how people make decisions.
Mm-hmm.
And it's a tough one. I'm sorry, it's Dan Ariely. Daniel Kahneman was the other one. The Thinking Fast, Thinking Slow. Dan Ariely, and I don't know how to spell it. Predictably Irrational.
In probably economy or business department. Okay.
Yeah, he probably is,
Okay.
right. And he found MIT graduate students to be wildly irrational. I mean, wildly irrational. He would run it, particularly in auctions. He would run an auction in the classroom
Right.
where he would have a list of items and a column for people to put down bids.
Right.
If you put your social security number in one of the columns, written as a dollar value, the last 4 digits of your social security number is a dollar value, just straight down the column, you would bid higher on everything. Because you saw this fake dollar number next to it, and you bid 25% higher.
That's funny.
Because you had an expectation
Right.
that had no connection with reality.
Right.
So this is really tough. Yeah, predictably irrational, that's it.
Can I see it? Daniel. Okay. Yeah.
So any theory of this, and I think Daniel Kahneman actually got a Nobel Prize for doing some of this work.
Mhm.
It has to deal with the psychology of the people that are paying the money.
Yeah.
And ultimately, there are people paying the money here who will decide how to do this, and that's really tough.
I think
Right.
it's all really tough, because even with that predictable rationality, there's non-predictable components, like sometimes I'm just lethargic and
Sure.
I'm not willing to do the little bit amount of activation energy hill to climb over to actually make that purchase or to do that thing, but maybe tomorrow I will be.
Right.
You can't predict that. It's not a matter of rational or irrational, it's a matter of I'm lazy today or not.
I mean, when you
have
want
my coffee.
Right.
If you
right
want to
then.
have a reference, if you want to have a
But if-
reference in one of your papers
right.
back to 1750, Benjamin Franklin had an essay on just this. It was called To a Gentleman on How to Pick Out a Mistress. And you would define values for these women by, each of the characteristics was to be assigned a point value, and you sum them up, you pick the one with the highest score. And any analysis of that would point out that he never used that technique himself, actually.
He had excess supply.
Well, there is that.
Talk about laziness, by the way, in this recently completed auction, the incentive auction that incented television broadcasters to give out their spectrum. The story that I've heard at a conference in Washington recently is that 10 broadcasters inadvertently forgot to hit the submit button and dropped out of the auction before they were ready.
Because they were probably too stressed out.
They
They were probably too stressed out.
That happens, but yeah, I mean, you're debating what dollar sign to put in here, and once the debate's over, they sit back and forget to hit the submit button.
Yep.
You wanted to ask you a question. You raised your hand, right? No.
No, I made a comment, but-
Sorry.
Okay.
Go ahead.
So, I guess the thing this highlights for me is that you've sort of shown a framework for moving from these estimated valuations to actually doing an allocation. But as everyone's saying, we don't really have a rigorous way to come up with the advertised valuations that you guys are proposing. So we're talking about various ways of trying to connect that to user experience in some way.
Okay.
So I'm just,
Go ahead.
I guess I'm curious about what new things this enables now that you've decoupled this decision-making between, say, the client device manufacturer and now the base station operator, instead of the coupled way that it's currently run?
Okay, so the idea is, basically, so these devices, they have valuations, and these valuations are not known, not to each other, not to the base station. The base station doesn't, the revelation principle that I discussed right here, it doesn't even tell you that, that the base station has to know the valuations, or the devices has to reveal their true valuations. Because the only thing they have to do is not to misrepresent their valuations. If you look at this function over here, this is the bidding strategy. This is the amount of bandwidth that the base station, that the device requires. X is the valuation of the device that it tries to misrepresent. It tries to hide, right? So what happens here is that the only thing that the revelation principle requires is that X is equal to nu I. The device doesn't have to tell anything to the base station about its own valuation. It just has to be truthful, so that this functionality between the amount of demanded bandwidth and amount of valuation, it's a correct relationship, basically, in the sense that BI, what I mean is, at the end of the day, it is BI that has to be declared to the base station, which is the function of the true valuation of devices. Right? So we don't even have to know the valuations of devices.
Okay. I guess the distinction I'm raising is this possibly misrepresented or non-truthful advertised valuation versus say the device has a poor estimate of its own valuation. Mm-hmm. Because as we said, we're having trouble describing what a correct valuation is.
Right. The correct valuation, no one knows about it. Only the device knows. We are estimating the valuations based on this formulation here that describes how much a device has to be charged based on not its true valuation, because who is charging the devices? The component that's charging the devices is the base station. Base station doesn't know anything about the ground truth valuation. It only can estimate it. If the base station follow this equality, and I didn't mention this, but find the valuations based on this equality. I didn't write it down. Based on an equality that the optimal multi-unit auction theory tells you that you plug the information for the demanded bandwidth and it gives you the valuation, then you will have the base station will be able to charge each device by this amount. But again, at the end of the day, everything depends on how precise we know the demand profile, how precise we know the PDF, the probability density function of the valuations, and many different factors, basically. So this truthfulness is just an idea that is not the fact that, like, in every single iteration devices are truthful. They are truthful in expectation term. They are truthful in ex entering meaning sense, right? So that is basically the definition of truthfulness here. So in one iteration, some of the devices may lie. In the other iteration, some of the devices may not even lie, may not be able to understand what their valuation is.
But if, base station in any case, again, if they pay, it's good for base station, but it's truth. Because in any case, if they want to cheat something, to gain some information extra, it's not good to be truthful, yes? But for base station, it's if just to be paid, it's
Okay.
for you, truthfulness here is not so important, really. If there is, user.
So what you are saying is why truthfulness is important?
For base station, just money important.
Okay.
Whether it's a good guy or not, for me, just dollars important.
Okay. now the answer to that question.
I can even gain more money if somebody of these guys cheated, because the other will also be paid.
Yeah, all we need is to allow our smartphones to charge the advertisers money to display their ads.
Good
We'll make money off it.
So, I can
That's right.
get my mind.
But the idea of truthfulness, I explained it here. It's revelation principle as the fact that if we can induce truthfulness, so then the optimal truthful mechanism is optimal mechanism in all classes. That's the reason we insist on inducing truthfulness, because we want a mechanism that's optimal all the times among all different kind of action mechanisms.
Maybe it will be work if, because you are here consider just one base station, yes, to reduce prices. You was talking about competition, so you have, put your model inside of, so it's the next level to it. There is a few base stations, they compete between the others, and truthfulness is important for them, because a user can move from one to the other, you your stories. So you have to, put your model inside of to at one more level.
Okay, I got it, yeah.
Otherwise, it's your story.
Inside the human level.
Yes, it does work. And truthfulness will be also
Okay, yeah.
important. For a while, it's not important. You can gain money.
This goes back to sort of Winston Churchill's statement, right? An auction is the worst possible way to allocate resources except for all others.
Did he say that, really?
No, well, he said that about democracy, but it fits here too.
Oh, okay.
It even sometimes is good for, base station, put some wrong guide and can increase it. So like game with
Right.
to send some money.
Right.
It's not good guide, and not top user. If there is no competition between base stations.
Okay, so
More questions?
Let's wrap up the seminar, and you can speak to a few
Sure.
people individually.
Thank you very much for attending, guys. I appreciate it.